Alcohols can be substituted to make alkyl halides. Alcohols can be eliminated to make alkenes. Alcohols can be oxidized, a special type of elimination, to make carbonyl compounds, COO compounds, ketones, aldehydes, carboxylic acids. Alcohols can act as nucleophiles, like in this reaction. In this reaction, my alcohol is going to act as a nucleophile. We don't officially have to know this mechanism for another couple of weeks, but we're going to go ahead and draw it now because I think it's helpful for you to see a mechanism more than once. Protonate the carbonyl oxygen, like so. This is an acid carboxylic acid mechanism. Carboxylic acid mechanisms are different from a lot of the others we've seen. The alcohol then acts as a nucleophile and attacks the carbonyl carbon, like that. Alcohol attacks the carbonyl carbon. You get this out of it. That O with a plus needs to be cleaned up. So some base in solution. We're going to call it water this go round. We'll talk about specifics later. Water comes to clean up. We get this. This is a neutral tetrahedral intermediate. Again, this is not something we need to know just yet, but I'm showing it to you anyway. We'll summarize momentarily. That tetrahedral intermediate is not super stable because you have a single carbon connected to 3 very electronegative oxygens. That's not going to hang around for long, so we protonate one of our OHs. Doesn't matter which one, protonate one of our OHs, and then we let that water go. When you let go of the water, you get a carbocation. What's super stable about this carbocation is it has resonance. Resonance of that carbocation looks like this. There's another very important, very good resonance picture, but I'm out of room down here, so I'm drawing just that one. And then I'm going to make a little bit of room for finishing off this mechanism. Some base comes to clean up. We're going to use water. We will explain details later. And ta-da! We make an ester. It's officially called an organic ester, but we make an ester. We're just going to call it an ester. So the take-home message, what you need to know from this reaction is when I add a carboxylic acid and an alcohol and some extra acid, I'm going to get an ester. You need to be able to predict the product of the ester. The way it always works is you lose the OH from the carboxylic acid and the H from the alcohol, and you connect the O to the C, like so. I'm going to lose the H from the alcohol, the OH from the carboxylic acid, and I connect the O to the C. This O, highlighted in red, is this O. Whatever is connected to that O comes along for the ride. So no matter what kind of alcohol you use here, the alcohol brings all of the carbons connected to it along for the ride to make your ester. This is an alcohol acting as a nucleophile to make an ester. This is an alcohol acting as a nucleophile to make an ester. It's just a shorter, different mechanism this time. This time, alcohol attacks first because we're not in acid. We're in base. Pyridine is a base. And I get this thing. Pyridine is my base that comes to clean up that oxygen with a plus. like so. And this is a tetrahedral intermediate. I fold down and kick out my leaving group, my Cl. Do we have to know this mechanism yet? No. The last mechanism and this mechanism are soon to come in Unit 3, actually. Soon to come, but I want to show it to you now because we're talking about oxygen acting as a nucleophile, alcohols acting as a nucleophile. The take-home message is so similar to the last one. What you need to know is this O becomes connected to the carbonyl carbon. And whatever is connected to your alcohol comes along for the ride. That's a CH3, even though that is totally not legible as a CH3. You lose an H and a Cl in the process. So you'll sometimes see that it's an ester plus HCl. You'll sometimes see that it's an ester plus pyridinium, pyridine with a plus, and Cl, pyridinium chloride, like that. Either way, it's the same thing. Alcohols act as nucleophiles. No matter what kind of alcohol this is, the carbons connected to it come along for the ride to help you make your ester. Okay? The last two mechanisms you don't have to know, but you need to be able to predict those products, this unit. So that was making what's called organic esters. This is making what's called an inorganic ester, more specifically, a sulfonate ester. A sulfonate ester looks similar to a regular organic ester that we've been talking about for a while, but it's a little bit different. Do we need to know this mechanism? Yes. Put a star on this page. You do need to know this mechanism. The way it works is the alcohol acts as a nucleophile and the alcohol attacks the sulfur. Folds up electrons onto that oxygen. Let's see if I can keep it color-coded. Like so. What do you suppose the pyridine is there for? It's there to clean up that oxygen that has a plus. Maybe this color blue is a closer shade. And then we fold down and kick out our leaving group. The Cl is our leaving group. And out of this, we got this compound. This compound is known as a sulfonate ester. So yes, you need to know this mechanism, and of course you need to be able to predict the products. Sulfonate esters are cool and interesting compounds because they themselves can then undergo SN1, SN2, E1, or E2 reactions. So hold that thought. Sulfonate esters. This is a very particular compound that we chose, this blue compound, where my laser's not showing up. This blue compound is a very particular compound that we chose to react with our alcohol. This blue compound is called tosyl chloride. It's going to show up eventually, I think. There we go. Tosyl chloride. Tosyl is actually a shortened name that is para-toluene sulfonyl chloride. So you want me to shorten the name to tosyl? Toluene sulfonyl. That's abbreviated tosyl chloride. Tosyl chloride is such a common reagent that it gets its own little acronym thingy. It's not an element on the periodic table, but it gets a capital T, little s thing like it's an element on the periodic table. TSCl, tosyl chloride. When you react tosyl chloride with this alcohol, you get this product, these products. Yeah, the pyridine cleaned up the proton. There's our color-coded. The H came from the alcohol. Oh, you can't see that. The H came from the alcohol. Oh, boy. H came from the alcohol. And the Cl came from the tosyl chloride. Yeah. The O got connected to the sulfur. This product over here is a tosylate. What is a tosylate? Oh, come on, PowerPoint. A tosylate, there we go. A tosylate is a sulfonate ester. It's a particular type of sulfonate ester where this part is connected to some carbon group. So note, a tosylate does include, when we talk about something being a tosylate, it does include this red oxygen that came from your alcohol. This is a tosylate. It's a methyl tosylate officially, this specific one, because we have a methyl group on the other side connected to my tosylate. Okay, so that group up in the corner can be abbreviated CH3OTS or TSOCH3, it doesn't matter. That's a methyl tosylate. There are other sulfonate ester forming compounds that are very popular. Tosyl chloride, very popular. Mesyl chloride is very popular. MsCl. MsCl is sulfur double bonded to oxygen with a chlorine and a methyl on one side. Mesyl stands for methane sulfonyl chloride, which gets shortened to mesyl chloride. When mesyl chloride reacts with an alcohol, it doesn't matter what kind of alcohol it is. When it reacts with an alcohol, you get a mesylate. A mesylate, that's the deuterium up there, would look like this. And we have an OMS on the other side. This is a mesylate. A mesylate with all the atoms shown is this. You got rid of the chlorine, you got rid of the hydrogen, and you hooked the sulfur and the oxygen together. Okay. Triflate is the last sulfonate ester forming thing we need to know. It's this. That stands for trifluoromethane sulfonyl chloride. Isn't it so thoughtful of organic chemists to call it triple instead? That's an F. That doesn't look like an F. Trifle. Trifyl. Triple chloride. Crazy, I know. Triple chloride can react with an alcohol. It doesn't matter what kind of alcohol it is. It can be this tertiary alcohol. It doesn't matter. Triple chloride reacts with it to create a triflate. That OTF, that's really O, sulfur, oxygen, oxygen, CF3. It's a triflate. Yep. You need to recognize the structures of tosyls, mesyls, and trifles. There are other sulfonate esters that exist, but those are just three of the most common sulfonate esters. So we said alcohols can act as nucleophiles, and we drew two mechanisms where alcohols were acting as nucleophiles to create organic esters. We said you're not yet responsible for those mechanisms, but you should be able to predict those products, and you should probably be able to use those in a synthesis, like making an ester in a synthesis or something, but no mechanism required yet. We then drew a mechanism of an alcohol acting as a nucleophile to make a sulfonate ester. We made a tosylate specifically in the mechanism we drew, but you're also responsible for the same mechanism to make a mesylate or a triflate. Mesylates, triflates, tosylates, those are the three most common sulfonate esters, but other sulfonate esters exist. Why do we care? What's the big deal? Well, sulfonate esters themselves, once you make a sulfonate ester, they possess a good leaving group. This thing that I'm circling is a good leaving group. OTF, a good leaving group. OMS, a good leaving group. OMS, a good leaving group. OTS, a good leaving group. We've already highlighted in orange up above. Sulfonate esters are good leaving groups. So they themselves can undergo SN1, SN2, E1, and E2. The cool news. Oh, this is such great news. These are such weak bases that they're on par with the same base strength as bromide, iodide, chloride kind of things. So what that means is they follow the exact same flow chart that alkyl halides follow, meaning primary SN2, secondary anions, yes, strong base, yes, E2, that kind of thing. They follow the same flow chart. Sulfonate esters follow the same alkyl halide flow chart. Alcohols do not do that. Sulfonate esters do. Well, let's put it into practice. When I add this alcohol to this tosyl chloride with pyridine, what do I get? I get a tosylate. Oh, PowerPoint. This tosylate, there we go. That H left, that Cl left, TS took the place of the H. Tosylate. You are responsible for that mechanism. Note, I did not react at the carbon over here whatsoever, so my stereochemistry stayed the same. So then I need to characterize. This tosylate is primary, secondary, tertiary methyl. This is a primary tosylate, a primary sulfonate ester. This is a primary alcohol. So when I substitute as a primary sulfonate ester, I'm considering that carbon right there, that carbon that's connected to this group, which is my sulfonate ester. Sulfonate esters are good leaving groups. So it's a primary sulfonate ester. The flow chart says primary SN2. When you add cyanide to this sulfonate ester, you're going to do an SN2 reaction. Carbon with a minus, attack the carbon that's partially positive due to the tosylate pulling on it. You can get rid of the tosylate. You should also get inversion of configuration because it's SN2, inversion. So this cyanide is now newly bonded. My deuterium and hydrogen swapped places because it was SN2, inversion. This is only one example that we're walking through with what to do with a sulfonate ester once you make it. But sulfonate esters are cool and important things that you should study. We're only walking through this one example because I can make this blanket statement that says sulfonate esters follow the flow chart. And that means I don't feel the need to walk through 8 million examples with you. Sulfonate esters follow the flow chart. So know that alkyl halide flow chart for the sake of alkyl halides, because I'm still going to test you on those, but also for the sake of sulfonate esters. If you know the flow chart, you know alcohols, you know, if you know the flow chart, you know alkyl halides, you know sulfonate esters, and what reactions they should do. Okay. All right. Sulfonate esters are inorganic esters. Phosphate esters are also inorganic esters. These are some of the phosphate ester examples where you've got 1 OR, 2 OR, 3 ORs. These kinds of compounds are very common in biological systems. Have you ever seen any phosphate esters in biological systems? Come on, PowerPoint. Have you ever seen phosphate esters in biological systems? Yeah, you have. ATP. I wish this were interactive so you could tell me where have you heard about ATP and what it does. Adenosine triphosphate. Yeah. This is a good leaving group. All this phosphate stuff is a good leaving group. This bond is very easily broken because it's a phosphate ester, just like those sulfonate esters. You can very easily break that bond. This is a primary carbon. So it's a primary phosphate ester. It's very good at being SN2'd. So water or something from our bodies can attack that thing and let go of that triphosphate compound, that triphosphate ester thing. That's not exactly how the energy breakdown works, but you can turn ATP into just adenosine that way. Phosphate esters are also what holds together all of our DNA bases. So it's got to be a reasonably stable compound, but you can also cleave DNA through reaction of all of these little primary CH2 phosphate ester linkages. Yeah. Taking a little detour to tell you, phosphates are good leaving groups. Phosphate esters are good leaving groups. Phosphate esters are good leaving groups. OPP, this abbreviation, OPP, that is this group, pyrophosphate. There's an enzyme in our body that isomerizes these two compounds, IPP and DMAP, into each other. You displace a hydrogen and a pi bond, and that's all that has happened. But that enzyme that isomerizes those two is important. Once you have some IPP and DMAP present in solution, something that can happen, we're drawing it as a fake little reaction, but hopefully you don't mind too much. Some base in solution, that's probably water under our physiological conditions, some base in solution can take a hydrogen. That hydrogen can dump in electrons toward that pi bond. Pi bond reaches out and attacks and ejects OPP. I'm drawing it like a weird little mechanism. This is a physiological thing that's happening. This is a little bit fake arrows, but a new carbon-carbon bond is created between this CH2 and this CH2. There it is. There's a reason I drew it in green. Those two CH2s are now connected. All right. You take one of these molecules and react it with another molecule of IPP, like so. Some base in solution, probably water under our physiological conditions, takes a hydrogen, dumps in electrons, that pi bond kicks out, and kicks out my good leaving group OPP. This was the new pi bond that got made in my last little reaction, my new sigma bond, my bad. This is my new sigma bond that got created in this new reaction, yeah? We use the same enzyme to do both of those reactions, but we've now got whatever you want to say that is, pyrophosphate, this thing, pyrophosphate, OPP, good leaving group. Take two of these molecules and add them together through another enzyme reaction. We're not actually going to attempt to draw this one and how it happens, but squalene synthase takes two of those molecules and hooks them up, makes this new sigma bond in the middle there, and you get squalene out of it. Squalene may or may not be something you've ever heard of, but squalene is the precursor to cholesterol. So in the beginning, this said the biosynthesis of cholesterol, part 1. Part 1 is OPP is a good leaving group, so you do several reactions where OPP leaves, pyrophosphate leaves, because it's a good leaving group. Then you end up with this squalene, which has a whole bunch of pi bonds, and in the next video, we will actually see how squalene becomes cholesterol. It looks real different from cholesterol right now, I know. That's alcohols reacting as nucleophiles. All right.